In this video, we'll go over the answer key for Friday, April 17th. And what we're talking about today is molar entropy. Remember, entropy is a measure of chaos. Well, we can actually give a numerical value to how much chaos an object has. That's called standard molar entropy. That is, 1 mole of stuff, what is your value of entropy? And that depends on what state you're in, how heavy you are, how many bonds you have. But this is an extensive property. That is, the more moles you have or the more stuff you have, the more standard entropy you have. And there are some trends for standard entropy. So if you look at the trend from a liquid to a gas, entropy increases. You become more chaotic in the gas. That's also for solids too. If you go from solid to liquid, you become more chaotic. Your entropy increases. If we're looking at weights, as long as things have the same number of bonds as we see here, entropy increases. So helium is the lightest, xenon is the heaviest noble gas. Xenon has the higher value of entropy. Now here, we're looking at bonds. So argon is heavier than NO. However, NO has a bond, argon doesn't. So NO is heavier. Same thing here with CO and C2H4. Same weight, but C2H4 has more bonds than carbon monoxide, so it gets a bigger value of entropy. When you dissolve a solid into aqueous, you are making your salt, in this case, more chaotic, so increase in entropy. Here, diamond and graphite, well, this one's interesting because diamond does have more bonds. However, the bonds are restricting the movement of the diamond in relation to the graphite. So here, two solids, same molecule. Graphite is a lot more mobile than diamond. That's why it's used in pencils, because when you press it, it'll flake off. So graphite has more entropy than diamond. So our first question is just to see from our molecules which one has a higher standard molar entropy. So I'll just run through all of these. So the aqueous version has a higher molar entropy than the solid. CH3 is heavier and has more bonds than CH4. Gas always has more entropy than liquid. Heavier gases have more entropy. Heavier gases as well here. Heavier and more bonds will have more entropy than SO2. All right. So during a chemical reaction, we can actually measure how much entropy changes, and this is called standard molar entropy. And the way we measure standard molar entropy is adding together the number of moles of a product, their standard entropy, minus the number of moles of a reactant times their standard entropy. So this is delta, so it's always products minus reactants. It's similar to delta G of reaction. We can calculate the standard change in delta G if we know the formations, product minus reactants. But right now, we're just worried about S, so we're going to look at how to calculate S. And yeah, so delta G equals delta H minus T delta S, but we're just going to focus on S right now. So calculate delta S reaction for each of those reactions. So I'm going to do A for us. We have C2H4 plus H2 goes to C2H6. Here's our reaction. The sum of the number of moles product times delta S product minus sum of number of moles reactant, S reactants. So really, I want to do products minus reactants. So C2H6, so that's 6 supposed to be small, minus C2H4 plus H2. These are going to be our standard entropy values. So C2H6, so I have a 1 here. That's because I have 1 mole of it. 1 mole times 229.2 minus 1 times 219.3 plus 1 times 130.7. So I'm going to add these two together before I subtract. And what I get is minus 93.8. And I don't have a unit here, but this probably should be joules. And this negative number makes sense. We took two gases and we combined them into one molecule. And we talked about earlier how that would decrease our chaos in our reaction. And that's it for this video. I will see you in the next video.